To find a relation between ordinary differential equation and partial differential equations. In fact, we can put an ordinary differential equation in a form of partial differential equations, and we can proceed. For example, we have a differential equation, so we will first start with the first order differential equation and then proceed further. Let we have a differential equation, simple one, uh, y dash equal to y, and we know solution of this different ODE is y is equal to e to the power x with some constant, but leaving the constant for time being. Now I am putting this differential equation in a partial differential equation. So the total differential operator can be used as uh, partial by partial x plus y dash partial by partial y and up to so on. But for our purpose, first order ODE, this is enough. So when I operate this on the solution space. So my solution space in the first order is some function of xy. Also I will operate this d by dx on the solution space f of x y. Equivalently, I will operate this same operator on that solution space, and if his solution of 1, then it must be 0. So what this give me? This give me fx plus y dash fy equal to 0. And by the characteristic method, we can write dx over 1 dy over y dash by I know y dash is y, in fact df ratio 0. So what is y dash? Y dash is y. I'm solving this one. So what we have? We have dx is equal to dy over y, because y dash is y, and you see x is equal to natural log of y, which give me e power x equal to y. This is the same answer we solved, we see from the beginning. So what is the concept in this case? You see, I consider a general solution space. If it is general solution space, then the operator d by dx will annihilate this function. So that concept give me, you see, this is so relate on this on the second slide. I have differential equation y dash equal to y. and the corresponding PDE is fx plus y dash fy equal to 0. Equivalently, fx plus y fy equal to 0 because y dash is y. So either dealing this differential equation or this partial differential equation, we have the same solution space. So I'm writing solution. Let me name it. This is the question 2 and this is 3. Solution space of 2 and 3 is the same. In other words, what is f? F of xy is, let's call it some constant c, is a solution of 2. This is solution of 2. F of xy is equal to c is a solution of 2. Let's see again. E power x minus y equal to 0. In this case it is 0, but it will not always be 0. So we ignore our integration constant in this case. So that is why it is 0. But if I incorporate the integration constant, then there will be some constant. So when you operate the dx on this c, you will get 0. You see, I operate d by dx on the solution space. It will give me ex and minus y dash, and you see what is y dash, that is y, and y is equal to ex, so that gives me 0. So I'm taking the solution space as f of xy for the PDE. So there is a deep connection between the ODE and PDE. Okay, but this is not a PDE. This is you see, this will be some algebraic equation because f is not algebraic because we now differentiate f with respect to x and y with respect to y. F with respect to y, so this is uh, first order PDE. So let's take another one. Let's say y dash is equal to y square. So we can solve this and we see, let's solve it. This is dy y square and dx, and that will give me minus 1 over y is equal to x plus some constant. So let's take this integration constant. This means y is minus 1 x plus c. This is my answer by the usual procedure of the ODE, and now you see that the constant is minus y 1 over y minus x is equal to c. So this is my function f of x y equal to constant, but let's take this as general. A solution space f of x y, I operate the differential operator on the solution space, and you see it is in the other form. Operate on f of x y, and if it is solution space, then it give me 0, and that give me fx plus y dash plus y dash is y square if y equal to 0. That is dx equal to dy y square equal to df ratio 0. Okay, you see this is the same thing over here, and you will get the same answer. Y is equal to minus 1 over x plus c. So you always convert your differential equation in the first order linear partial differential equation, and you will get the same result. So where is the goal? The goal is in fact this coefficient. You see my tangent vector is always, in this case my tangent vector is let me write the PDE equal to 0. So what is tangent here? The tangent vector is 1, here is 1, and y dash, but this y dash will always be some function of x y. So you will have the tangent vector 1 in omega always. This is the tangent vector, and I have some space, and in my case is a curve, and we have a tangent vector which is this thing. So the whole knowledge is encoded in this omega. You get that omega from the, you pick that omega from the differential equation and make your tangent vector, tangent space, and then proceed the calculation. So you get this is the tangent space, and you integrate it. You see in the previous slides we integrated here. So if is a constant, and that constant must be equal to this c anyhow. Okay, so that is the goal. Let's consider a second order, and for time being so what will be my result? My result, I will take a differential equation of any order, and I will convert that into a linear first order differential equation, and I will get a tangent vector, and then tangent vector be integrated to get the original solution space. So let's consider another example of double dash, and let's say known 1 equal to 0. We see the solution of this can be written in this form: y is equal to some c1, and let's say I'm writing in sine, so sine sin x plus some c2. This is the answer. You can put it in the other way as well. C1 sin x cos c2 plus cos x sin c2. So in fact c1 and cos c2 is constant and sin x plus c1 sin c2 is a constant cos x. So it is usual then when you put a1 sin x, a2 cos x, and we usually write the solution of this equation as this solution. Now let's try the new method. We convert it into we convert this into the partial differential equation. So I am taking the solution space now to be a function of x, y, and y dash. That will be my solution space. Sometime the solution space, solution space or first integral. Okay, I will operate, if it is the solution space, when I operate the operator, which in other form is y double dash y dash operated on this function. You see why writing this one, because it's not a function of xy only, it is a function of xy and y dash. And if it is a solution space, then it will give me 0. Another one, if it is a solution or first integral of the given differential equation, then this must give me 0. But you see, what is y double dash? Y double dash is minus y from my equation I take. See here. Now what this equation tell me? This equation tell me that fx plus y dash fy plus y, let me take y double dash fy dash equal to 0, but I will put y double dash at minus y. So the equation, the partial differential equation corresponding to the given equation is this one. Now we see that the characteristic equation is dx over 1 dy over 1 y dash equal to d y dash over minus y equal to df ratio 0. This is the characteristic equation. Now let's solve it. Dx1 dy y dash and dy dash minus y df 0. So f will always be a constant. Let's call it I. In this case, I will get 2 phi i's because we have two equations. So let's solve this one. In any other combination of these three will give me another one. So I'm taking this is simple one, so that is solvable already. Yeah, it implies that minus y dy equal to d or y dash dy dash. What this give me? This give me minus y square over 2 is equal to, so let me put a constant over here, that is phi 1, constant of integration, and y dash, let me put it to c1, so I will multiply it with 2. So what this give me? This give me c1 with 2 time is equal to y square plus y dash square, and that is phi 1. This is first integral, and it is a function generally of x y y dash. In this case it is y square plus y dash square. So this is let's say 4 equation. This is one first integral. Now I need second first integral from this equation. So what I have to do, I will take some combination of these two with this one. So what is that combination? You see, I can write this equation, so I am writing it again in this. So I will multiply with y dash dy, it will be y dash square equal to minus y dy dash by y square. So by component divide into concept, we can add them. So let me do it on the other side. Dx must be equal to add the two, this with this one and this with this one. So that is y dash dy minus y dy dash y dash square plus y square. Okay, you can put it in this way: y dash square by y dash square plus y square, and y dash dy minus y dy dash over y dash square. And some other simplification, I am writing this one over 1 plus y square y dash square into y square dy y dy dash y dash square. So if we look at this carefully, this is the derivative, the differential of tan inverse y by y dash. So when you integrate it, we'll get some phi 1 plus x. This is, let's take it to is equal to, so let me take it c2 so that I will get phi 2 is equal to tan inverse y over y dash, and after simplification, rearranging, phi 2 is equal to x minus tan inverse y by dash. Okay, so this is phi 2. So now I find phi 1 in phi 2. Now the other goal is to find the solution. These are first integral. You see we have to integral phi 1, which is y square plus y dash square. The other one, phi 2, is x minus tan inverse y dash. And we have to find y solution. So what we have to eliminate y dash from these two. So let's do it. I write this equation as can be written as tan inverse y dash equal to x minus phi 2, and phi over y dash is tan x minus phi 2. Okay, so what is y? In fact, I need y dash so that I eliminate it from the game. Okay, so let's find y dash from here. Y dash is y over tan x minus phi 2. So I will put this y dash over here, and let's see it on the other page. Phi 1 is y square, and y dash square is now, what is y dash? This is y square over tan square x minus phi 2. It will be y square 1 plus 1 over tan square x minus phi 2. Okay, and that is equal to tan square x minus phi 2 plus 1 over tan square x minus phi 2. And this whole is multiplied with y square. Okay, so what is y square? Y square is tan square x minus phi 2 over tan square x minus phi 2 plus 1 with phi 1. So we can convert it into using trigonometry. We see that tan square theta plus 1 is secant square theta. So I will use this identity. That will give me y square 10 square x minus phi 2 over secant square x minus phi 2 with phi 1. Now what is this? This is in fact, you will see it's 10 is sine square x minus phi 2 cos square x minus phi 2, and the secant is up cos square x minus phi. This whole is multiplied with phi 1 and these two cancel. So when you take the root, this will be phi 1 1 over under root 2 sine x minus phi 2. And you see they are constant, so I can write this as a constant. So this is the solution we find earlier in usual way. So what this is, what the message is. The message is this one, that a partial differential equation, this one, is equivalent to the original differential equation because they give the same information, they give the same solution. So at the end, I am concluding my my video. If I have an nth order differential equation in this form, n minus 1, I can relate this with the partial differential equation first order partial. So this will be related to the first order partial by partial x y dash partial by partial y double dash partial by partial y dash up to yn. So I will put yn as omega partial by partial y n minus 1, and it will operate on the solution space, which will be function of x y y dash up to yn minus 1. So this equation will give me n first integrals in variable x y y dash up to yn minus 1. So we have to eliminate these derivative variables. So how many are there? There are n minus 1. So we have inequation and have to eliminate n minus 1 variable. Is a good system and you will solve it. For example, in the previous slide we have n2, so we have two equations. You see that we have two equations. One is this one equation, second equation, and we have to eliminate one variable, which is y dash. So in two equations you have one variable to be eliminated. In three equations you will have to eliminate two variable y dash and y double dash. And if you have you have n equations in n first integrals, and you have to eliminate n minus 1 variable, and you will do that easily. So that is the relation between ODE and a PDE of first order linear. First order linear. So it is easy to deal a first order linear differential equation than to deal an nth order differential equation. Nth order ordinary differential equation. Thank you very much.